This program has this one feature I really hated. There's a checkbox. You got to check if you want to record the video for YouTube, and I forget to check it all the time. So I think I missed one of your lectures, and I forget to check the box. But they ought to have it. It should be checked by default, and you should have to uncheck it if you don't want to record it. So if I don't remember to press the button, then I don't get a recorded video, and that kind of messes up. So I don't know if it was you or the other class I didn't record the video for, but anyway, that's on me. So if I had a piece of wire, a conductor, and I hook it up to a battery, so current flows through the conductor. Now, in your book, he'll show current coming out of the negative going into the positive. And I think I mentioned in class, the way I show current is the other way. I show current coming out of the positive going into the negative. If I show it that way, the current would move like that. That's called conventional current flow. Current actually goes the other way, but this idea of conventional current flow has current coming out of the positive side of the battery and going into the negative for reasons I don't want to get into right now. So it's important because if we use the other way, the way your book does it, that's called electron flow, then what I'm going to say is not valid for that. You have to change some things around. So just understand, basically, use my notes for what we're talking about for any kind of questions I might have for you. So I got a wire, piece of copper. I got a battery. I hook it up. Current's going to flow like this. Now, if I want to, let me see if I need some kind of hold on one second. All right, so if I want to show direction, if I want to show direction, I can show it with an arrow, right? I can show something going this way, like I did for current. I can show it going this way or that way. I can draw it in the plane of the board any direction, basically. How would I draw it, though, if I want to show something coming towards you, like towards the camera? In other words, for this arrow, say this is your eyeball. That's your eyeball. If you see the point of that arrow, the way I'm going to draw that, something coming towards you, it's like if this is the arrow, and I turn it towards you, you're looking at the tip of the arrow, you're looking at this. If I want to show the tip of the arrow, I'm going to show a circle with a dot. That's the tip of the arrow. If you're looking at the other end, so if your eyeball is over here, you're looking at that end, the way I'm going to draw it is like that. So now I can draw direction. I can show direction in the plane on the board with these arrows. But I can show something coming out of the board at you with that, or going into the board away from you with that. So that's important for what I'm going to talk about. Because there's something called the right hand rule I want to talk about. Now, if you use your book, again, don't use your book for this stuff. He's going to talk about the left hand rule because he's using electron flow. So just to keep it simple, just use my notes for this subject. And then you can go back to the book if you want to. So, one of the things you got to be able to do for this conductor is basically tell me the direction of the magnetic field around the conductor. Remember, anytime I have current flowing, that current is going to create a magnetic field. We talked about that in the last video, or the last class. So if I have a current flowing through a conductor, it's going to create a magnetic field. And the question I want to answer is, all right, what does that magnetic field look like? The cool thing about this is, remember, we use B for flux density. And when we talk about the magnetic field, that's what we're talking about. We're talking about the flux density. So, because current creates magnetic field or flux density, I'm going to write this. The magnetic field is directly proportional to the current that causes it. That's what makes this so cool, because if I have a lot of current, I can have a really strong magnetic field. If I reduce my current, I can have a reduced magnetic field. Basically, I have a magnet whose magnetism I can control, and as I said a few seconds ago, you're going to find out that's very, very, very useful. But how does the magnetic field look around this conductor? Well, if you have physics, some of you have physics, some of you didn't. If you didn't, it's not a big deal. But you talked about something called a vector, and the other is a scalar. Now, what's a vector? Well, in physics, they teach you that some numbers have direction and magnitude. That's a vector. Some numbers just have a size, just a scalar. So an example of a scalar would be like the temperature. I don't know what it is outside right now, but it was pretty nice yesterday. I think it got up to like 70 or something. That's just a number. That would be a scalar quantity. A vector would be like a force. I have a certain amount of force in a certain direction. I have to have two pieces of information to talk about force. The size of the force, maybe 10 pounds of force, and the direction that that force is acting. That's a vector quantity. Well, it turns out you can do math with vectors, and when you multiply vectors, there's something in physics called a cross product and a dot product. So if you didn't have physics, or if you had physics and they didn't talk about this, it's not a big deal. But if you have physics, what we want to do is we're doing what they call the cross product in physics. And people don't have that kind of background. Some people do, some people don't. So instead of getting into cross product and dot product and all that math stuff, they do something that makes this really, really simple. They use something called the right-hand rule. And that's what I want to show you. The right-hand rule. And what this is a simple way to do a cross product, multiplying two vectors together. So what I'm doing is this. Imagine that I have this magnet. I got this magnet, north and south, and you know now that the north, coming out of the north, is this line of force that comes up like that and goes into the south pole, actually goes all the way through the magnet, but it has direction. So if you're looking at this, if this is your eyeball, you see that north pole coming towards you. What you see is this. So I'm going to represent this magnet basically with an arrow. I'm going to say that this is the same as this. I'm going to represent the arrow, and that north pole is like right here, and that south pole is right there. And if you're looking down at this north pole, this is your eyeball, and what you see is this. If you're looking up at this south pole, you see the magnetic flux going away from you. What you see is this. So I'm making use of this dot notation. This is now north pole. This is a south pole. So if you understand that, what you can do is this. If I have a conductor with a current flowing through it, and I want to know, all right, what does the magnetic field look like around that conductor? It's actually circulating around the conductor, either clockwise or counterclockwise. But what does it look like? Which direction is it going? You can take your right hand, and what you do is you put your thumb in the direction of current flow. Now remember, conventional current flow. We always use conventional current flow. You put your thumb in the direction of conventional current flow, and you wrap your fingers around the conductor with your thumb against the conductor like that. And the tips of your fingers, from pointing at you like that, is basically that. It's like a north pole coming toward you. If I point into the board like that, then you're looking at the north pole leaving you, or you're looking at the south pole. So I want to know, what is the north-south pole distribution around this conductor? What does it look like? I put my thumb in the direction of conventional current flow. I wrap my fingers around the conductor like that. And then what you see is I have my fingertips coming out at the top. So here are my north poles. Those are dots. Here are my south poles. Those are X's. Like that. And so what I have, basically, if this is my conductor, the magnetic field is doing this. It's moving this way. If I turn it toward you, it's moving like that. So I actually have a magnetic field. If I draw it, if I draw the conductor, so you're looking at the edge of the conductor now. Here's your eyeball. You see this, and that magnetic field is doing this. So that magnetic flux is actually going like that. And the current, if this is your eyeball, you see the current leaving your eyeball, you show it as an X, the current. So I'm using this dot X notation to show the direction of magnetic flux or current. So again, the right-hand rule, you got to be able to do this. The right-hand rule, you take your thumb, put it in the direction of conventional current flow. You wrap your fingers around the conductor, kind of like you're hitchhiking. And the top of my fingers come out on the top. So my north poles are on the top, my south poles are on the bottom, and the magnetic field is circulating like that. I'll turn around like that is clockwise. Now you might say, all right, what happens if I reverse the current? If I reverse the current, watch what happens. Current goes that way. Now my north's on the bottom, my souths are on the top. And that's actually pretty cool because I can reverse current, which means I can control the magnetic polarity, the north-south pole. I can control that around the conductor. Anything I can control physically like this, we can do something with it. So this turns out to be pretty important. The idea of the right-hand rule and able to determine the direction of the magnetic field around a current-carrying conductor. Now, let's take this conductor. Often, what they'll do is they won't have a straight conductor when they deal with electromagnetism. They won't have a straight conductor. They'll take the conductor and they'll wrap it around into a coil. So it'll look like this. So instead of having a straight conductor, what if I had this? Okay, so I got a voltage source and the switch, and I got the wire now, and it's coiled. Well, basically what you do when you take a wire, the wire has magnetic flux all the way down it. When you coil it, what you do is you take that flux and you put it into a smaller area. You concentrate. So by taking the wire and making it into a coil, you get a stronger magnetic flux, a stronger magnetic field. And it turns out that that magnetic field looks like this. Where this is the North Pole and this is the South Pole. And you might wonder what's so special about that, but if you remember from our last conversation, that looks exactly like the magnetic field around the bar magnet. The difference is because of this, since that magnetic field is directly related to the current that creates it or causes it, because of that, if I increase, say I have a variable source, I can turn the voltage up and down, that'll increase my current. I can actually have a stronger or weaker magnetic field depending on how I adjust my voltage. And if current is flowing this way, when I close the switch and I get a north pole here, south pole here, if I flip the battery over, then what happens is the north pole and south pole will reverse. Again, anything that I can control, I can make that useful. That's what engineering does. Engineering takes science and makes it useful to mankind. So the question is, all right, what can I do with this? What can I make with this? How can I apply this to solve a problem? And it turns out that a whole lot of different devices are based on this. I want to explore just a couple. One thing you can do with this, if you can understand how this works, I want you to imagine, for a second, I have a paper towel roll. I think I have some paper towels. Yeah, so I got some paper towels. If I take the roll out of here, the little cardboard thing in here, if I take that out, I got a tube, a cardboard tube. And if I wrap that cardboard tube with some wire, so let's say I wrap wire around this, a bunch of coils of wires, and bring it out like that. And over here I got a battery, and again I got a switch. If I close the switch and current flows through the coil, I get that magnetic flux around this. And what I end up with is something that looks similar to this. All right? So I have like North Pole here and South Pole there. Well, what you can do, this is just something I thought up in my head, but just to so you can see how this works. What if I dropped another magnet in here? I guess this will show up. Let me try the red marker to see if that shows up. What if I drop another magnet in here like this? I'm going to move that North Pole for a second. If I drop another magnet in here like this, and that's a north, and maybe that's a south. Yeah, I think that'll work. I attach a rod here, and that rod could be connected to something. When I close this, if this is the North Pole, if this is the South Pole, when I close the switch, current flows, and this becomes the South Pole. If that's the North Pole, it's going to pull this plunger down into the tube. If I reverse the battery, this becomes the North Pole, and I got a north against the north, it's going to push it up. So I can cause something to move magnetically. This is exactly what happens if you have power door locks in your car. There's two types of power door locks. Some of the higher end cars have vacuum locks, works on air, but the majority of all cars will have a situation where they have basically a solenoid type situation like this, where they use magnetic flux to move something up or down, back and forth. And that's exactly what they use this for. You can have your door lock mechanism here, and you can reverse the polarity by moving the switch back and forth. It reverses the polarity of the current, which changes the north-south orientation of the coil, which either, if I have a north against the north, is going to push the plunger up. If I have a north against the south, it's going to pull the plunger down. Any kind of motion, linear motion like that, any kind of linear motion, I can use this device to make something move. Maybe you've seen locks work this way. A locking mechanism. You have a doorbell you push, and it pulls a lever back so you can open the door based on this. So it's a lot of devices based on this idea of electromagnetism. So there's one application for you. Now I want to talk about another one, and this is important, but it's a little hard to explain. So hopefully you guys can follow what I'm going to do here. So I'm going to explain another application of this electromagnetism called motor action. Motor action. Now, for motor action, you got to understand say if I have get some different colors here, it's a little easier to understand. So say if I have a bunch of, I don't know, let's vector field. So I got a bunch of little vectors, maybe forces, or I don't know what you want to use as an example, but I think you'll get it. Look at this. If I have a bunch of, let's say, forces acting in this way, these are my, if you can see the colors on the camera, these are my purple forces. So I got some force acting like that, and I got the force acting like that. And let's say they're actually acting on an object. They're actually acting on an object, then the purple and the green are going to add together. I got 3 purples and 2 greens. This field of vectors, this field of directional numbers, they act together. The point is they're additive. So I get what you call a strong field. A stronger field because they work together, they're additive. Whereas if I turn this around so that the green vectors or the green forces, or however you want to think about it, if they're working this way, if I get a vector field like this, and I got another vector field working against it, well, these two guys, if they're equal, are going to take the bottom 2 out, and I'll end up with just a 1. So what I end up with is a field that's weaker. I get a weak field. Weak. I get a weak field. So if I have basically forces acting together, I get stronger force. If I have forces acting against each other, I get weaker force. So if you understand that concept, and this is actually pretty simple, I want you to try to follow what I'm going to do. Now, normally, if we weren't doing this remote thing, I would give this as part of the exam, and you'd have to explain motor action to me. I don't know. I don't even think I gave you guys exam 2 yet. I don't think I gave it to you. I gave the other night class exam 2, but I didn't give it to you. They kicked me out of school before I had a chance to send it to you. I had it made up, and I've been promising it to you. But anyway, we'll worry about that another time. So look at this. Instead of having, I showed you a straight conductor with current going through it, and we can use the right-hand rule to figure out the direction of magnetic polarity around it. What I'm going to do now is I'm going to bend this wire into basically a coil. I'm going to bend the wire into a coil. So instead of having a straight wire, what if I bent it so that it looks like this? And instead of having a straight wire, where I take the battery and put on it like that, I'm going to put the battery right here. And if I put the battery right there, then what's going to happen is basically current is going to flow out of the battery into the conductor, and then this wire is going to go this, going to go down like this, and then back here, and eventually back to the battery. So what I want to do is, I want to use the right-hand rule on the top conductor and the bottom conductor. I'm going to shade these in. So I'm interested in not this part. The conductor actually does this. Right? It looks like that. So I don't really care about this part. Matter of fact, I'm going to take that out of the picture. It's still there. Just imagine it's still there, but I only want you to focus on the top and bottom. So let me take this and move it over because I want to refer to something, and I need to draw something over here. So let me redraw this over to the side. So I got my conductor over here. I'll put it down lower to get out of that glare. So here's my conductor. Like that. And I got my battery like that. And what I said was current is in And this top conductor, which we'll call conductor A, this is conductor B. And that top conductor, I got current moving this way, and then the bottom conductor is returning like that. That's current flow. So what I want to do is over here, I'm going to get two magnets, two permanent magnets. I'm going to set them up like this. And the north pole here and the south pole there. If I do that, and the magnets are close enough, then what I'll have is magnetic flux moving from one magnet to the other in that direction, north to south. That's the way flux flows from north to south, like that. So what I'm going to do is I'm going to take my conductor, my coil. I'm going to take it. I'm going to turn it towards you. So remember, conductor A is on the top, conductor B is on the bottom, and this cross piece I don't really care about. So I'm going to take my conductor, I'm going to turn it towards you, I'm going to spin it this way, and then I'm going to get rid of that middle. The middle is still there. I just want you to imagine it's still there, but I just want you to focus on this one and this one, conductor A and conductor B. So if I do that, if I take my conductor, my coil, I turn it around like this. Now, what you're going to do is you're going to look at, if you're looking at conductor A, what you see is current coming toward you. In conductor A, current coming toward your eyeball, you'll see that. You'll see the tip of the arrow, the tip of that arrow. If your eyeball is down here and you're looking at conductor B, you see current going away from your eyeball, you'll see the X. It's moving away from your eyeball. So if you remember that, when I take my coil, I'm going to turn it around toward you and spin it this way and just get rid of the middle part so that it doesn't have to get in our way. What I'm going to do is take the conductors and stick them in that magnetic field. If I do that, then I end up with conductor A right here and conductor B right there. And we already said that the current in conductor A, if you're looking at the edge of it, is coming towards your eyeball. So in this picture, I will put a dot. If you're looking at conductor B in this picture, it's moving away from your eyeball. The current is going into conductor B. So in this picture, it's going out of A into the cross part that I'm not showing, back into the board. I got to show an X. So now the dot and the X don't represent the flux flow. Now in this situation, the dot and the X represent the direction of the current, either coming out of conductor A or going into conductor B. Now what I want you to do, I don't know if you have this drawn on your papers or not, but what I want you to do is use the right-hand rule on both conductor A and conductor B and tell me the direction of the flux around each of those conductors. I'll give you a second to think about it and to draw it. I want to know the direction of the flux around A and the direction of the flux around B using the right-hand rule. See if you can do that. So the way you think about that is you take your right hand, you put your thumb in the direction, your thumb always shows conventional current flow. You take your right hand, you put your thumb in the direction of conventional current flow, which in conductor A is out of the board, coming toward you. And your fingers are going to wrap around the way that the flux arrows are spinning. So on the top, the flux is going like this. And on the bottom, the flux is going like this, using the right-hand rule. If I do the same thing for conductor B, this time the current is going into the board, like that. So on the top, it looks like the arrow is this way. And on the bottom, of course, is the opposite way. So since the current is coming this way in conductor A, the flux is rotating counterclockwise. It's going this way in conductor B, it's rotating clockwise. But remember the thing I showed you about the vector field. Anytime I have vectors or forces working together, they're additive. If I have them working in opposite directions, it makes a weaker area around it. So this is a strong force. If everything's working together, it's a weaker area, weaker force if they're working against each other. So notice right here at the top of conductor A, the red, I don't know if you guys can see these colors. I don't know how well that camera is picking these colors up. But this is red. And the flux from these fixed magnets moving over here to the right. So I got the red flux from conductor A going the opposite direction of the black flux from the fixed magnets. I have a situation where the fields are canceling each other out. So it creates what we call a weak field right there. And on the bottom, it's just the opposite. I have the flux from the coil and the flux from the permanent magnet acting in the same direction. So this is a strong field down here. I got weak field and strong field below the conductor A. And over here with conductor B is just the opposite. On top, I see that the green flux from the coil is acting in the same direction as the fixed flux from the permanent magnet. They're working together. So I get a strong field here, and here they're working against each other. I get a weak field here. Now, this thing right here, if it's free to move, if it's free to spin, what's going to happen is I have basically strong to weak. Strong to weak. There's going to be a net force this way, and strong to weak, a net force this way. And if this coil is free to move, if I have a force this way and this way on a rigid object that's free to move, it's going to put a torque on it and it's going to cause it to spin. And that's called motor action. That's motor action, very important. All basic DC motors work on this principle. This thing will just spin around. Now, if we were at the school, I actually have a motor that I built. I took a coil, I took a magnet, permanent magnet. It was a kit. I didn't build it from scratch. It's a kit. But I built this little motor, and I will demonstrate it to you. Here you can see we have a lot of control, because if I have this polarity for my current, I'll get one rotation. In this case, this rotation is this way, clockwise. But if I flip the battery over, then this thing will reverse direction. If I increase the current by turning the voltage up or down, I can control the speed at which this thing will rotate. So motor action is very, very, very important. Now, see, I'm out of time here. I got like 1 minute left. There was a video I showed at the beginning of this. I'm recording this, but I didn't record that video. I'm going to send that link out when I put this video up on YouTube, because there's another part to this. I want to talk about the opposite of motor action is something called generator action. Generator action. Let me write that down for you. Generator action. And this is actually based on the video, what the guy did in the video. So I'll send that link out, and I don't know how well that video played through Blackboard. I'm going to put the link out. You can go directly to it, and before the next class, you can watch that video again. When we get back together, I'm going to talk about generator action, and we'll tie these two together. And this actually gets us into the final part of the course. Since we've been together, we've been talking about DC circuits, direct current. Well, this actually gets us into something called AC, alternating current, alternating voltage. This is a segue into it, this generator action. So we'll talk about that next time. Now, as a matter of the exam, I don't know if I have a PDF. I just literally, I grabbed the stuff out of my office, threw it in the box, and some of the stuff I got that I needed for class, some of it I didn't. I went and I bought a camera, I bought some drywall or green wall, whatever you call this stuff, and a whiteboard. And I threw this stuff together. So I actually had your exam 2 prepared for quite some time. I just don't think I ever handed it out to you. So I'm hoping that I have a PDF version I can just put out on Blackboard. If I don't have the capability to scan anything here at my house. And I know there's an app that you can use on your phone to take pictures. I don't have a cell phone. So I want to get that test to you so you can start working on it. But in the event that I can't give you a PDF copy, I'm probably going to write it by hand on the board or something like that. I just want to get some problems to you that you work. Because we're supposed to have 4 tests, and we're running out of time. Because of school closure, I want to make sure we stay on course. So we'll worry about that next class, though. I'll see you guys on Wednesday. And by Wednesday, I'll have some kind of exam put together for you, and we'll work it out. And anybody have any questions for me before we sign off? Okay, I guess you don't. If you don't, again, I'll put this on YouTube. I think the first video didn't get saved, so I need to re-record that. If you missed that, I'll make a video about what that is and put it up there. That way you can review the section before this. And then I plan on Wednesday doing the exam. I'll have something for you for the exam, and then we'll move on from there. If you have any questions, send me a text or email. And you guys have a great rest of the day. And I will see you same time on Wednesday.